Inverse functions. So inverse functions are going to be very useful for us for solving equations. And we've been using inverse functions all along. We're just not really aware of it because it's not usually phrased that way. So for instance, if we have y equals 3x, this is equivalent to saying that x equals 1/3 y. And the reason that is because the operation of dividing by 3 undoes the operation of multiplying by 3. And we're going to see this as we start talking about inverse functions. We can write it on the left or we can write it on the right by switching the roles of the variables when we switch to the inverse function. And we also could do y equals square root of x. Well, that's equivalent to x equals y squared. Because squaring and square root are inverse functions. And the ones that we are going to be using explicitly, that we will be talking about as inverse functions, are exponential and logs are inverse functions of each other, and then we have the trig and inverse trig. So we have if y equals e to the x, that's equivalent to x equals natural log of y. Now that one was done base e. We can do exponentials and logs in any base. So if y equals a to the x, that's going to be equivalent to x equals log base a of y. And we can do the same thing with the trig functions. If y equals sine x, then x equals sine inverse of y. So we have the identity that y equals e to the x is equivalent to x equals natural log of y. And we can use this to solve exponential equations. For example, if we have e to the 3x equals 7, we have an equation that is similar to this, except the x has been replaced by 3x, and the y has been replaced by 7. So we come back over here and we make the same replacement. So x is being replaced by 3x, and y is being replaced by 7. And so now we can finish solving this. Divide both sides by 3. We get x equals 1/3 natural log of 7. Or we can bring that coefficient inside and make it an exponent. So this is going to be 7 to the 1/3. Or we can write it as cube root of 7. Any of these three expressions would be a good way to leave your answer, and it really kind of depends on what you're trying to accomplish with the problem. We can do the same thing if we have a log equation, and log equations are kind of nice also because if we have multiple logs, we can use the properties of logs to bring them together. So say we have natural log of x squared equals natural log of x plus 9. Okay? In the case of log functions, if we have multiple logs, what we want to do is we want to move them all over to the same side of the equation and then combine them into a single log, and then we can use the property to get the variable out of the log function. Okay, so this is going to be natural log of x squared minus natural log of x equals 9, which means natural log of x squared divided by x, since we're subtracting, equals 9. So simplifying there, we get natural log of x equals 9. But that's equivalent to saying that x equals e to the 9. So when you are using this property of the inverse function, the function moves over to the other side and switches to the inverse function. Okay, so we can do the same thing with the trig functions. If we have sine of 7 theta equals 1/2, this is going to be equivalent to 7 theta equals sine inverse of 1/2. And now from here we can divide by 7, and we get theta equals sine inverse of 1/2 over 7. Now, looking at our unit circle here, we have sine inverse of 1/2. Now, you have to be careful when you're doing this with trig functions because sine equals 1/2 twice on the unit circle. So there's going to be one in the first quadrant and one in the second quadrant. But sine inverse only has one solution here. And the one solution for sine is going to be in the first and fourth quadrant, no matter what value is inside here. In this case, it's a positive 1/2, which is going to be right here. So this is going to be pi over 6 divided by 7, which is pi over 42. However, this misses a solution because it loses this solution over here. So you have to be careful when you're using this method to solve trig functions if you're using the inverse trig there, because of the fact that the trig functions have multiple solutions.